of the talk, lies, damn lies and statistics. It's because we're in the middle of an election. And we've got lots of politicians running around making lots of promises and using lots of facts and saying that they're going to invest so many millions or billions in the economy. And so this particular quotation is often ascribed to a famous British politician called Benjamin Disraeli from an awful long time ago. He probably didn't say it first, it might have even been Mark Twain, but who cares? It's a saying that's come into British society, and you hear it often used by people who are frightened of statistics. They're not very comfortable about using statistics. And I guess that means about half of the room. Some of you will be very happy using statistics, others will be very frightened of it, and some of you will know more about statistics than I do, some of you will know less. So I've got a little challenge today to try and give everybody in the room something, even though they might be quite happy playing with statistics, or even though this might be a class that they wish they could avoid. But we'll see how we get on. So the menu for today, quick introduction to really statistical testing in management research, and some of the topics that I'm going to be looking at: significance, correlation, regression. Deanna's already mentioned experimental design, so I thought I'd spend a bit of time looking at what he meant by that. T-tests is where a lot of this kicked off when we asked me what the heck the difference was between a T-test and a One-Way Anova. So for Wing's benefit, we're going to cover that one. But the T-test is probably one of the most fundamental statistical tests that you guys will ever use, and one or two of you I know have already used that. And some of you will have used SPSS before, some of you won't. So for those of you who've never seen SPSS or never wanted to see SPSS before, then I've got an actual data set. The data set is from a paper that Wing, I and Phil Harris are working on. So it's real data. So by the end of it, I hope even those of you who have a pretty good understanding of statistics will have the opportunity of stepping back and having a look at some of the assumptions we make when we're using stats in management research. Those of you who, this is a bit of a horror story as a 2-hour session, you don't expect to enjoy it at all. I hope that you'll get something from it. This is the sort of thing that you run into. It's a joke, it's meant to be a joke. Statistics is a precise and logical method for stating a half-truth inaccurately. So we're surrounded by statistics. Marketing is often about statistics. Our product is 69% better, 75% of people said they preferred it, and so it goes on and on and on. People throwing statistics at you, and when you read an academic paper, the chances are, if it's a quantitative paper, there will be some statistical tests in there which try and justify what's going on. And sometimes it can be quite unnerving as to exactly how valid some of these statistical tests and claims are. So let's jump straight in with this lovely word, significance. What exactly does 95% confidence mean? It means that in 5 out of 100 times, it won't happen. So we expect it to happen 95% of the time, but 5% of the time we get a shock. We get a shock. But statisticians, it's like learning a different language. When we express that mathematically, we say p equals less than 0.05. So we want to be confident, so a big number is better, but we express it as in p-values, where the smaller the number is, the better. Now, in management research, 95% confidence is perfectly okay. That's adequate. In some research areas, 99% confidence is okay. In others, 90% confidence is okay. So a lot of sociologists are comfortable, sociological journals are perfectly happy for p-values to be 0.1, 90% confidence, whereas in some other journals they get a bit sniffy at 95% confidence. But for most management journals, 95% is okay. So what on earth does 95% mean in practice? I understand that Chinese people sometimes like to gamble. Is that true? Okay. So you might meet someone that says to you, heads or tails? Heads, it's tails, I'm sorry. You've lost your money already. Heads or tails? Heads, it's tails, I'm sorry. So you've lost your money again. Now it starts to get interesting. Okay, heads or tails?
Head.
It's a tail. There's a head on the other side, just to prove there is a head. That's 3 in a row. That's 3 in a row. Now, Wing is checking already after 3. Remember that. Remember that. Remember that. Because we'll bring it back to 95% confidence in this again. Oops. Okay, call it. Or did you see it? I'll toss it again.
Tails.
Tails. So
Yeah.
you switched.
Yeah.
You switched. And you're right.
Oh. It's always.
But,
Why?
amazingly, and I didn't fix this, we've had 4 tails in a row. So even though every time we toss a coin, there's a 50% chance, the probability of a head is 0.5, the probability of a tail is 0.5, we are 50% confident we'll get a head, we're 50% confident we'll get a tail. When we have 4 in a row, we can do it slightly differently. We can say that really what we expected is slightly different. So hopefully, where's the calculator? So let's have a look at the chances of getting 4 tails in a row, which we've just got. So the first time it's 0.5 times 0.5. So the chances of getting... hang on. I hope not. Let's cancel that. There we go. 0.5 times 0.5 equals 0.25. So the probability of 2 tails in a row is 0.25, because we could have had 2 heads, a tail and a head and a tail, or 2 tails. So the probability of getting 2 tails in a row was only 25%. How about 3 tails in a row? 0.06. 0.06. And Wings then, as a management researcher, intuitively correct, because she's interested in 95% confidence. And this is 94% confidence. So 94% confidence, there's something wrong with the money. Gary has fiddled this somehow. But he hadn't, amazingly. I've never seen 4 tails come up in a row in my life. Let's see the chances of that. The chances of that are only 3 times in 100. 0.03. So a management researcher would say, what we've just seen is not possible. We would reject it. So when you're doing a statistical test and you are happy with 95% confidence, that's what you're saying. That's what you're saying. I'm 95% confident this is correct. Only 5% of me says it's wrong. And you are betting your thesis, your life, whatever it is that you're working on, that 95% is perfectly adequate. When you see that, 4 tails in a row, you start to think, oh dear, maybe 95% isn't as good as I thought it was. So, 99%, let's have a look at what would happen the next time we're now down to 99%. So another tail. Let's try it. Let's try it. It's a tail again.
Wow.
It's a tail again. I should do this for a living, shouldn't I? I make a lot of money. I make a lot of money. There's something must be wrong with those with those coins. So if you do gamble, I've seen Wing in gambling in a casino in Manchester. No, I haven't. And she always bets on red because red is a lucky colour in China. So puts all her money on red every time. If you get 5 reds in a row, it's a fix. It's a fix. It's a fix because the chances of that happening, somebody's got a magnet underneath that roulette wheel. So you have my permission, Wing, to shoot the croupier. You will not be convicted of murder. I promise you, you will not be convicted of murder. Very bad joke. So 95% or 0.05 sounds better than 0.01. It isn't. 0.01, we're 99% now confident that what we're looking at is okay. So let's move on and have a look at variance and standard deviation, and the issue then of how do you test whether one group in your database is different significantly or not from another. And to do that, I'm going to use this slide, and this is data from 1,000 students. Somebody measured the temperature of 1,000 students and put it down as a histogram or distribution graph. And statisticians love data like this because it approximates to a normal distribution curve. What's a normal distribution curve? Something which looks like that. So if you go back, here we have actual data, and it's a bit spiky. There's a bit sticking up on the right-hand side, so it's not quite normal. But when we have a look at Wing and I's data later on, you might think this is actually pretty good data. And the beauty of a normal distribution curve is that we can put limits on it to decide whether or not people are unusually hot or unusually cold. So 37 is the average temperature that's okay. We think that's okay. 37.5 is fever. So if somebody has the temperature is 37.5, now clearly 37.5, which is something over here, isn't part of this population. So we can be very confident that this lot are okay. But what about that person there, or these two people there? There will be a natural variation within any population. If you've just had a big meal, if it's a hot meal, if you just drunk a hot cup of coffee, if you just drunk a cold drink, that will make some variation in the data. There's a variation between males and females, there's a variation by age. But that may or may not explain these people at the two extremes. So if we think of it in terms of standard deviations, this lovely word standard deviation, the horizontal axis is now converted to something called a standard deviation. And on the next slide, if you want to cheat and have a look at that, there's a mathematical formula for how you calculate a standard deviation. And that's the sort of thing that puts students right off. They don't like squiggles and square root signs, and they suddenly blog. An easier way of thinking about this statistic called a standard deviation is that a standard deviation either side of the average or the mean includes 68%, i.e. roughly two-thirds of all the data. If you go up to 2 standard deviations, you get 95%. And that's why you'll hear statisticians saying, we're 95% confident that this is okay, this is part of the normal population, because it's somewhere between those two extremes. We don't need the formula to calculate standard deviation. Looking at it that way, I can then say roughly that is 95% of all the data. So between 36.95 and 37.05, so that 0.05 then is 2 standard deviations or whatever. So you can estimate what the standard deviation is. So the standard deviation just defines how fat that curve is. So a bigger standard deviation, that would move over there, smaller standard deviation, it would cut in. But the standard deviation defines that distribution. That's why statisticians get so excited about standard deviations. So if you were to consider those people on the edge, think back to the other one, these people who've got a particularly high or particularly low temperature, by comparison with the group, seem to be on the edge of the group. So we could say that we are, particularly if they're way out from 3 standard deviations, if they're part of this, we are now 0.003, the probability of 0.003, but there's something wrong with these people. So we would, if we were a medic, we would say, your temperature could be okay, but it's either high enough or it's low enough that we want to have another look at you. And that, if you were a medic, you'd be using 99.7% confidence limits. If you're a little bit more conservative, then you might drop it down to 95. If you're a mum or a dad, you start to worry if the temperature goes outside quite a narrow range. You then check on it in 10 minutes. So what's the temperature now? Do this. My mother, bless her, when she got ill, her temperature dropped. With me, my temperature goes up. So you can have illnesses going in either directions. So we can use a standard deviation then quite easily to check on a whole population, and we can say if fever is 37.5 over here, that is way outside of that distribution. Therefore, that group of students are not suffering from fever, because their distribution of temperatures is way, way away from a single point. So we can test how far a distribution is, whatever it is that we're measuring. Here we're measuring temperature away from a fixed point. What you often do when doing research is to test whether 2 distributions are similar or not. For example, we could cut this data into males and females. We could cut it by age to see whether or not there is, in theory, women's temperatures are slightly higher than men's. Is that true of this group? Is that true of this group? In theory, older people's temperatures are lower than the mean. Is that true of this group? So we can test the theory against this data set. Are you still with me? So that's the formula for standard deviation. So if you're happier using that than my sort of rather folksy interpretation, well, you can see roughly what a standard deviation is, because it includes 2 standard deviations either side is 95%. So sigma is the notation used by statisticians for a standard deviation, and that is the square root of the sum of each measurement, take away the mean, squared, divided by the total number in your sample. And that will give you the standard deviation precisely. So when you plug it into SPSS and out comes the answer, that formula there is embedded within SPSS. Or you can just put it in your mind and think the bigger the standard deviation, the more scatter, the more noise there is in the data, the fatter the curve. And variance is just the square of the standard deviation. So when people say variance, they mean standard deviation. The words are almost the same, and variance is perhaps the word in English is better than a standard deviation. Standard deviation sounds something sexual. It isn't. Variance sounds something to do with stats. So if you're happy with variance, then fine. If not, if your mind was blown by that slide, forget it. You don't need to know that. Right. So now we have two distribution curves, beautifully drawn. And they never look like this in practice. But what we want to know is, are they different? Maybe this is the data for males and females on the temperature chart. And how do we decide whether or not these two curves are different? And the easiest way to do that is using something called the t-test. And the easiest way of doing that is to actually show you what that looks like. And the beauty of the t-test, I said earlier that the data I had was 1,000 students' temperatures. You only need 6 cases in one and 6 cases in another. So if you've got 6 men, 6 women, 6 old guys, 6 young guys, you can start comparing them using what's called a t-test. It's better to have a big sample, as I'll show you. Bigger samples, but you can start with quite small numbers, and it can be meaningful. There is an assumption that your data fits one of these beautiful curves, and it never does. I've never seen a perfectly normal distribution curve before in my life. There's always some noise in the distribution curves. So what we're trying to do when we test is whether or not, what are the chances that these two curves, even though they look separate, are really part of the same family. We do it by looking at the differences between the mean or between the variance. And one is called a t-test and one is called a One-Way Anova. But they give you exactly the same result. So if you're using a One-Way Anova, if you're using a t-test, it will give you exactly the same result. And we'll check that in a minute. And what we're testing is, are the males and the females in this temperature profile, are their temperatures significantly different or not? At 95% or what have you? That's the basis of the t-test, and so we'll have a look at that in a minute. That's the formula for the t-test. Do you need to know it? Or do you use SPSS like a computer game? Like I do. I'm not a statistician. I cannot remember things like that. But some people love these sort of formulae. They dream about them. I don't. I don't. So I trust SPSS that when I give it some numbers, it will give me the right answer. I'll show you some tricks that you can sort of satisfy yourself that you're not being misled by SPSS. SPSS can make mistakes. There are versions of SPSS that have been shown on certain computers to have rounding errors, which occasionally will give you the wrong answer. One chance in a million, but occasionally, just occasionally, you will get the wrong answer. Here's another thing that we might be interested in. We might be interested in comparing these two distributions. They have exactly the same mean, but one is fatter than another. So which has the higher standard deviation, the red line or the blue line? Anybody disagree? Anybody dare disagree with me? It's the red line, isn't it? It's the red line. Good. You were listening. Now, when you are testing something, it's quite nice when you see data like this. So maybe we're looking at the relationship between age and temperature. If we get a line like that, we will be happy. We will be happy. For two reasons. One, when we analyse this data on SPSS, it tells us that the regression is significant or the correlation is significant. When you have just two variables, age and temperature, regression and correlation mean exactly the same thing. But statisticians love to have fun with us. They invent this new language. So they'll refer to a dependent and an independent variable. And I can never remember which is which. The dependent variable is usually the one we plot on the vertical axis. In here it would be temperature. Temperature is a function of age. Temperature depends upon age. So it depends upon age, therefore temperature is the dependent variable, and age is the independent variable. That's the only way I can ever remember it. And you can have more than one independent variable. We could put gender in as well. So the fit of this line and the test to see whether or not that line is significant or not will depend upon the same sort of statistics that we've been looking at. The reason for giving you this graph is to show you this one. One of the problems on SPSS is that SPSS is not a human being, it's a number package. And it will tell you that that relationship is significant. Even though, if you took that point right up in the top right-hand corner away, that line would become almost horizontal, and there is no relationship between them. There's no relationship. I nearly got the sack for this when I used to work for Mars, the confectionery and food group. Way back in those days, very few people could program and use computers. I could. The company just bought this new computer, but nobody could use it, apart from one or two of us. So I started producing lots of mathematical models, because loads and loads of data. And the key issue was the Mars bar becoming less attractive to customers? And my theory was that we were chucking too much of the trimming. So when you make a sweet like a Mars bar, you have cutters that cut the stuff you're making into strips, and the bits that fall off the edge, you chuck it back into the mix. So when you're making another mix, it all goes back in. And the amount of stuff that we were putting back into the mix was going up and up and up as a percentage. So I thought, well, let's test this to see if there's a relationship between the amount of stuff that we're reworking and the consumer satisfaction evaluations for the Mars bars over 30 years. And I found there was a significant and downward relationship. The more rework we were using, down came the evaluations. But fortunately, before this paper went up to the main board, somebody checked my data and said, Gary, depends upon one data point. Depends upon one data point. So that little story always puts into my mind the need to have a look at your data. Have a look to see what it looks like sooner or later. Unfortunately, SPSS has a great graphics package. It's not easy to use, but once you've solved it, it's quite a nice little thing to have a look at. So I'm skipping through correlation and regression quite quickly. You don't want to spend a great deal of time on it, just to make the point that you need to be careful with your data. So here's another joke, just to cleanse your mind. So believe me, a p-value of greater than 0.05 indicates your chance of drowning is not significant. When you're using statistics, when you're using things like p-values and 0.05s, it's a language. And we communicate that with using that language with other people who understand it. but sometimes the people we're trying to talk to don't understand it. Don't understand it. Even people like me that have been around for years occasionally make errors in analysing data. Occasionally make errors in analysing data. So assume nothing when using your statistics. So, just an introduction to the data that we're going to be having a look at today. The research question that Phil Ring and I were considering was, if you have a business, a small business, say, and it's owned and managed by family members, do you tell customers that you're a family business? Is there any marketing benefit in telling them that you're a family business? So Diane's work is saying, okay, let's look at what MEs are saying about themselves to the marketplace. Are they saying we're trustworthy? Are they saying we're competent? Are they saying I went to an upmarket university, signalling status? Another signal that an ME might give to the marketplace: we're a family. We're a family. People that work here, all members of the same family. In China, signalling family business is a positive or a negative? Don't answer. Yes, it's a negative. So in this, the literature though says it's a positive. The literature says it's positive.
We don't know anything.
So it doesn't. So theory says that we judge a business automatically for whether we think it's warm, competent, effective, and status. You heard that already this morning. Theory also says that family businesses are more successful because they're seen as more friendly, i.e. warm. So people have tested how people see family businesses using this sort of theory. And family businesses generally tend to be seen as warmer, more friendly, more supportive, but not as competent as non-family businesses. But today I'm just going to focus on warmth. So I hypothesis, telling people that your family business will improve your evaluations for being warm. Is everybody with me? Because the next bit is not going to make any sense. So this is an experimental design. So 4 groups of people. Online survey, market research company, organising a panel of potential respondents. We created a fictitious company. It was either a gift business or a grocery business. So half of our sample were told that this business sells gifts, and the other half were told this business is a grocery business. We told everybody the same basic information: grocery business, gift business, and a bit more. Then we measured how warm the business appeared to be using these items. I think I would trust the new company. I would expect the new company would be warm and friendly to deal with. I think the company would behave ethically. I would expect they would make a positive contribution to the local community. These are all items that have been used to assess the warmth of an organisation in previous research. So, one group of people were just told about the business. They were not told whether it was family or not. They were not told if it was small or not, the other thing that we were testing. Another group was told, in addition to the basic information, that it was a family business. Another group were told, in addition to the basic information, it was a small business. And the final group were told, in addition to the basic information, that it was small and family. We were told both. And that's a classic experimental design. What's it look like? So this is exactly the information people were given. The new company sells a range of gift products, or it could be grocery, to consumers through its shops and on the internet. While the business is new to your area, it's been trading in other parts of the country for some years. The business has a range of products at various prices and tries to appeal to all age groups. You know that some friends of yours have made purchases from the company, but you don't know much more about them. So the group that just got the basic information just were given that. The company is a family business and owned and managed by its founders. That's the family business signal. So another group got the basic information plus that, the red stuff. Another group then got the company is relatively small, less than 100 employees, as signalling small. And then the final group got both of those. And the market research company changed the order in which the final group, so half of them got one bit, the family bit first, the other half got the small bit, just in case there was what are known as order effects. So, let me end that and open SPSS up. What you've got is our full database, which includes other bits and bobs. I've cut some of the variables out, but there are about 1,000 respondents in this database. We're only going to use about 2/3 of it this morning. But this is what an SPSS database looks like. So it looks like a spreadsheet, in that it's got numbers in these boxes. Some have got decimal points, some haven't. There's missing values here. That's a mistake of mine. Don't worry about it. Age, that doesn't mean that person is 5 years old. It means that they've ticked that particular box. Gender. So unlike an ordinary spreadsheet, we can give these variables names, which is quite helpful. SPSS, this is what's called the data view in SPSS. If you click on the variable view, have a go. You've now got a list of all the variables. And it's going to take some time then on this to familiarise you with exactly what we've got. All of these variables, the study number, the version of the questionnaire, whether they were told family or not, whether they were told small or not, the 4 measures of warmth, age, gender, and then the calculation variable warmth, they're all numeric. They're all number variables. But if you click inside one of these, please do, a little box comes up, and it means that you can change that. Probably the only relevant one is string. Again, it's another language. String means words. So if you've got a question on your questionnaire where people can write in an answer, then SPSS deal with that. It won't analyse it like NVivo can, but you can do some basic analyses, or you can capture that information and then analyse it using NVivo. You can use data, you can play with it to your heart's content. I don't want you to get befuddled, confused by how sophisticated SPSS is. It is an extremely sophisticated analytical tool. If you want your own personal package that you were to buy, it would cost you £2,000 a year as a license fee. That's how valuable it is. It's the #1 analysis package in the world. It was purchased 20 years ago by IBM, and they've made a lot of money out of it. So let's go down to this variable warmth and say, okay, I want to, instead of 2 decimal points, I want to change that. If you go to the data view, there's this warmth calculation, which is, I'll show you in a minute, is the average of these 4 here. But it's got the number 4.25 here. Say we wanted a little bit more than that, we could go into this and say, okay, let's have 4 decimal places. Back to the data view, and it's there. So it is storing numbers much in greater detail than it looks. So Some of the things that this computer package does, I'm still finding out. It's just amazing what's somewhere in it. If you then, you've made that change, that little box there is the most important one. Time after time after time, I close SPSS down, or the computer crashes, or the battery goes flat on my laptop, and I've forgotten to save the bloody thing. One or two of you have heard me talking about SPSS before, and so hang on, Gary. The first thing that you told us to do was to number all the cases, because you're going to be playing around here. And you know, who is respondent number 1, respondent number 2. So somewhere, when the market research company sends me the data, they send me a file with no respondent numbers on it. There's respondent IDs, usually the IP address of the respondent that you're not supposed to share. So there's something identifying those respondents. But say I want to put a number in. Well, the easiest way to do that, of course, is to right-click on there and click Insert Variable. And I put number 1 in there, number 2, number 3, I keep on typing until I get to a number 1,000. Easy? No. Number SPSS cases, click on it, and then come down to this archived thing here. And you will find this little bit of programming highlighted, copied back into SPSS, and then I want you to open another file, new syntax, and then paste that series of commands into syntax. The run thing there, or the easiest way to understand what you're doing, is to highlight it and push that green button. So either use the run command, and if you're lucky it does it in the right order, or treat SPSS as an idiot, highlight what you're trying to do, and then push the little green button. If we go back into the SPSS file, we've now got a new variable created called ID, and thank goodness, because I don't like to look a complete fool when I'm teaching, we've now got all the cases suitably numbered. So, the first time you create your SPSS database, label the cases, as we've just done, save it, open it under a different name, and only use that. Keep your original data untouched. Never analyze your original database. Copy it, save it, email it to yourself, put it on a memory stick, or whatever you want. Remember, under the UK Data Protection Act, you're not allowed to take that data outside the country. You can now forget I said that. If you've got human data, you've got the names of people, you're not allowed to take it abroad. So any names on it, take the names off. You've got now the number of your questionnaire, so you don't need people's names. Get rid of that. You've just got the ID, and number 1 on your database is number 1 questionnaire, number 2 is number 2, and so on. Now, let's say that we want to remember that ID means identity. What we can do is go back into the variable name, and in that label we can type identity. And then every time we look at those variables, it will give us the label, which might be a little bit easier to remember. So let me have a look at that. So under label, if you stretch that out, market research company, when they gave us the database, they copied and pasted the actual question on the questionnaire into the label. And that's a fairly common practice. So you know exactly what it is that that particular variable refers to. So question number 1, I think I would trust a new company just based upon the information, and then please answer the following questions, blah, blah, blah. So remember from the previous slide, that's one of my warm questions, just assessing how warm or otherwise that company would be. And under values, let's stretch the values thing out a little bit. If I click on one of those, a little blue box comes up, and you can see then it's a 7-point scale, and you can see what the values were. And you can type those in. Again, I didn't have to bother because that came automatically from the market research company. But for those of you doing your own database, you would manually type them in. The value 1 means strongly disagree, so you put the label strongly disagree, then you click OK, and then you go to the next one, and so on until you've built up the complete picture. So under age, we've got 6 possible boxes, all labelled up, so we didn't actually collect the individual's actual age, but we collected people don't mind ticking boxes. If you actually ask for their actual age, a lot of people don't like doing that. I've no idea why. It just tells people I'm the same age as Donald Trump. That seems to satisfy them. They can work the rest out themselves. So let's have a look at that age variable. Analyze descriptive statistics, frequencies. Where's age? Stick age in and click. So what did I do? In the database, doesn't matter if I'm in the database. Analyze is where you go for all your most of your work. Frequencies or descriptives, pretty similar. Frequencies is what I'm interested in doing. I moved the age one across here, and I've got lots of things I can play with here. So, only 2 people in the database were less than 20 years old, and you can work out the numbers yourself. It gives you the percentage, the cumulative percentage, and so on. So pretty much people tend to be bunched up here. One of the reasons for playing with the data, analysing the data to start with, as soon as you start doing correlations, you'll start getting excited. Oh, there's a correlation with age. Hang on, you've only got 2 people in this box. You've only got 5. You've got 58 there. That might be okay. So maybe you would have to combine these first 2 boxes. Otherwise, you'll get the nearly got sacked from Mars situation where 2 people are defining that data point. If you go back into the data set again, so these are the 4 questions that we asked to work out how warm people saw the company. And the first thing that you would need to check is, does that work as a scale? Does it work as a measurement scale? And some of you will have heard of something called Cronbach alpha. There's actually somebody called Cronbach that came out with a mathematical way of identifying whether different measurement items are useful for different scales. Why do we bother with scales? bluntly, to make the data more normal. If you just ask one question, you tend to get a non-normal distribution. If you have lots of different questions, it starts to approximate to a normal distribution. But we'll have a look at this in a minute. So how did I calculate warmth from those 4 variables, those 4 questions, and was I entitled to do so? And again, it's getting used to the language of SPSS. Analyse, scale, reliability analysis. You pop those 4 questions in. 2, 3, 4. Or if you're more sensible, you highlight them and move them backwards and forwards. You can highlight and move. All sorts of fun games. So I'm using Cronbach Alpha, deciding whether or not this works using Cronbach Alpha. But to get it to do anything, I need to click on Statistics. So click on Statistics, Item, Scale, Scale if item, deleted. Why do we need all 3? Don't ask me. It doesn't do anything useful unless you do that. Are you with me? Okay, then you go back in, you click OK, and you get some output. Now, room full of intelligent students, what's a good Cronbach Alpha? Do you know from memory? What are you looking for? You remember? 0.7 and above is okay. 0.8 and above is good. 0.9 and above is very good. 1, a Cronbach Alpha 1 would mean that everybody is responding to the same items. So everybody is responding to different items in the same way. So if they clicked number 4 for the first question, they click 4 for all the others. They click 5, they click 5 for all the others. So it's how consistently they responded to the scale is what we're looking for. So the first thing that we might notice is that the excluded numbers, because I didn't copy and paste all the questions across my mistake, but even with that mistake, the Cronbach Alpha is 0.83, which is pretty good. Pretty good. But what it's also telling me is if giving me some stuff there I don't necessarily need to talk about, but if I come down to this table, it's telling me if I didn't use that question, I'd get an even better Cronbach Alpha. It would go up from 0.83 to 0.87. But I quite like that question. I would trust, this wonderful word, trust. So I'm going to keep it in. I haven't told Wing this until today. She didn't know this until today, because she trusts me. So I've kept that in, and that's a sort of decision that you might be making. But what I can tell from doing this little analysis is that it's worthwhile then calculating this variable warmth using the average of these 4 questions. Explain better. You've got 4 questions, each on a 7-point scale. So person number 1 likes this company. They're going to rate them highly for warmth. So they're going to be clicking the 6 or 7 box on the survey. Okay. So Cronbach Alpha measures how consistently they respond to each of these 4 questions. So a Cronbach Alpha 1 would mean that they click the 6 box for each of the 4 questions. If they clicked 6 for 3 of them and 7 for another, that would lower the Cronbach Alpha slightly.
So So it seems to me it's the relationship between the questions.
Yes. If you ask the same question 4 times, the Cronbach alpha should be 1.
Yeah, that's right. So why does it matter?
Because you if I put how competent do you think this company would be in, it wouldn't be measuring the same thing. So Cronbach alpha calculation would tell me there's something wrong with this item. And I'd look at it and say, oh yeah, that's measuring competence. I'll use that for the competence measure.
So the lower the score, it means that they're less reliable.
Correct. You want a high figure. You want, most of the time you want above 0.9. But above 0.8 is perfectly acceptable. Some people will quote Cronbach alphas as low as 0.6. 0.5 means random. So, to 0.6. But there are lots of ways of validating a scale. You can use AMOS, structural equation modelling, you can use average variance extracted, so lots of other statistics. So if any of you ever get stuck with a scale and you want some fancy measure that proves that you can use the scale, come and see me. I'll find a statistic that you can use. But the simplest one, the one that everybody quotes, is the Cronbach alpha. Cronbach alpha. So that's the easiest way of remembering it, I suppose. If you ask the same question 4 times or 7 times, how many items on the scale, then you should get a Cronbach alpha of 1. If you ask completely different answers, questions which had no relationships to each other, it would be 0.5 or below. Cronbach alpha. If you have a negative question, say instead of I think I would trust the new company, say the question was I think I would distrust the company, you'd have to reverse code that question. So reverse code means a 7 means a 1, a 6 means a 2, 5 means a 3. You calculate it by saying 1 minus whatever it is equals a new variable. So if you get a really dodgy Cronbach alpha, it probably means that one of your questions needs flipping, needs reverse coding. That's Cronbach alpha. Other statistics, it doesn't matter. If people like something, no matter what you ask them, they'll be positive. So there's a danger that you can ask questions which don't seem to be overlapping at all, and it gives you a reasonable Cronbach alpha. So you've got to look at the questions and use your common sense as well. If I'm reviewing a paper, the first thing I look at is the scale. I'm not bothered about what they're claiming to measure. I look at the scale they've used, and that really tells me what they've been measuring. So the warmth figure is the average. So I need to go. If you look at these things at the top here, this is output. You can save this file. So we've got the syntax file, we've got the data file, we've got the output file. We can save this. If you want to copy and paste it into a report or a document, there's all sorts of fun and games you can have. But I don't want to completely confuse you today, or I don't want to completely confuse myself. But if you look at this at the top here, this banner at the top, you can do some of your analysis within here, but there's not something called transform here. To get that, you've got to be within the actual database itself. Transform, compute. So go back to the actual database itself and type in a variable called WARM2.
Transform and then what?
So you click on transform and then compute, and that brings you up the dialog box that you can see on the screen, and declare a new variable, target variable is what it's called, warm2. So we're going to recalculate warmth, but I'm just going to show you how it's done. warm 2, and in this numeric expression box we're going to put the calculation, and you can type it in or you can use these keys down here and these function groups over here. You can have days of fun just with this dialog box if that's the sort of thing that turns you on. So I'm going to say if I want to calculate an average, I need brackets because I'm going to put what I'm going to take an average of inside there, and then going to click on the first question, move it across, and then I'm going to add. I'm going to click on the next question, move it across, add, third question, move it across, add, fourth question, move it across, and I don't need add. So those are the 4 questions, each on its 1 to 7 scale, and I want the average, so I divide it /4. Got 4 questions, divide it /4. Yeah. If you want to save that calculation, click the paste button. So it pastes it to a syntax file. So you can save that syntax file, call it whatever you like, and it's quite good because then you can remember the calculation that you actually did to declare that variable warm2. So we know how to use syntax files. We highlight whatever it is we want to use. We click the green button, and hopefully in the database we've got something called warm2. If we go into the data view, we've got warm2. As I said, my apologies, I haven't put the questions in there, so we've got to come down a bit. And fortunately, the numbers in the box are the same as the numbers under warmth. So, to demonstrate how to recalculate, some of you looking at, hey, hang on, there's more decimal points. But you know how to put more decimal points in if you want. There's no point because maximum number. So if you don't want to use that anymore, you don't want to go warmth, you can cut it like that, or you can go into variable view and you can cut it like that. Clear, it's gone. Edit, undo, it's back again. Right, now I've got gender in here. Let's have a look at how many males and females I've got. Descriptive statistics, frequencies, gender, female, male, roughly equal. Females I've coded 1 because women always come first. 1 or 2 people are laughing at my jokes this one. Not many though, not many. Can you get me a better group of students for next time? And number 2, in life, are the men. So roughly equal. So, how do we tell whether the males are evaluating this company, these fictitious companies, more positively on warmth or less positively on warmth? The test we're going to use is a t-test. Remember from the graphic, so I'll go back. We're trying to test this. We're going to be looking at the difference between the distribution of marks given by men and the distribution of marks given by women to see if they are significantly different. Actually, the test is of whether they are the same. But I shouldn't have said that because it's like confusing myself. So if we go into, where's the database? Here's the database. Analyze, compare means. And then we've got a lot independent sample t-test. Because we've got two samples, we've got men and women, we use the independent sample because the samples are independent of each other. If you want to look at you've got two measures of warmth, you want to compare them, you have to use the one sample t-test. But usually you'll be using the independent sample t-test. We're comparing two groups which are independent of each other. So, go into the independent sample t-test. We want to compare warmth, shove it in, and we want to use gender as the comparison. Shove that one in, and then it asks us, well, hang on, which do you want to compare? Because you might have got three genders in. Male, female, other. And we don't want the others in, so we just want to compare the males with females. So we have to remember the codes that we gave those different groups. And even though we've only got two groups, we still have to tell it, because it's stupid, we still have to tell it groups 1 and 2. You there with me? And you click OK. And up comes, it's done it for all the data, 2013. Whether the warmth figures are the same or not, it gives me the figures we already know, how many men, how many women. It gives me the group statistics, that females on average evaluated warmth at 4.93, whereas males were a bit mean and rated these two businesses at 4.71. Now, are they significantly different? This is where the first confusion starts. So, warmth, equal variance is assumed, equal variance is not assumed. And here's a test that tells you whether you can assume that or not. The Levine Test. The Levine Test can be useful for testing whether the variances between two groups are. But all we want here is to know which of these two lines can we use. You've just got to remember it. If that significance is low, less than 0.05, you've got to go down a line. It means that the variances are different. It doesn't tell you. It should tell you. So get it in your mind, write it down in your notes somewhere. If that significance level is low, drop down to the second test, which is tougher. Slightly tougher. Here it doesn't matter because they're both highly significant. 0.05 is the threshold. Anything less than 0.05, we're there. We're there. If we want to know exactly what that number is, we click on it. And it'll tell us it's 0.000239. So try that. So I want to know what that number really is. Double click, hold it, and you're there. And you found that out last week that it did that. So there's loads of things that SPSS does. It's amazing. So, males and females have different results, and it is significantly different. Let's try a different test. Analyze, compare means, One-Way Anova. So this is to answer Wing's question of last week. What the heck's the difference? It's easier to use because we don't have to type in 1 or 2. So we've got warmth, comparing the genders, click OK. And it gives us the same result, 0.00239 in terms of significant. But now, instead of a t-test, we have an f-test. And one should be the square of the other. So that figure, 13.58, should be t times t. Anybody want to check that? 3.686 times 3.686 should be 13.58. But the f-test is measuring a slightly different thing, but mathematically, when you just got two variables, it's exactly the same. So this was a paper that Bing was writing with a Chinese academic. I think it was him. He was using One-Way Anova, wasn't he? He was not using the t-test. So that caused a bit of confusion. It took me about half an hour to work out, but it didn't make a blind bit of difference, but there we go. So why bother with a One-Way Anova if you've got a t-test or the other way round? Well, a One-Way Anova is particularly useful if you have more than two groups you want to compare. And in this database we've got age. So if I go into age, go back into analyze, descriptive statistics, compare means, One-Way Anova. So I'm back in the same dialog box, but instead of gender, I pop in age. I've now got 5 or 6 categories. So I'm asking the computer, is any one of those age groups different from any of the others? So are there any age differences that I should be thinking about or worrying about? Everybody with me as to where we're up to? You click OK, and down the bottom we're told that significance is 0.823, which means it ain't significant. There are no differences between those groups, even though we've only got 2 people in the below 20 group. There are no differences between those groups. If we did get a difference, all it means is there is a difference somewhere. It doesn't tell us where. What we've got to now do is to go back, rerun it again, compare means, independent sample t-test, One-Way Anova, and we now want post hoc. So I've clicked on post hoc, which means after. Why they start introducing Latin? It's just, and I want what I will always pronounce as Turkey. It's not Turkey. And then OK. And now it compares each of the age groups with each of the other age groups. So if we did get a significant result using the Turkey two-key statistic. It's very seasonal, isn't it? It's not one of those garage jokes. So didn't you laugh, because you always laugh at me. But so, a few minutes ago we decided that men and women were evaluating warmth differently. But what I always told you to do was check the data. Check the data. So, let's have a look at graphs and chart builder. Don't show this again. So graphs and chart builder. And I want a histogram. So come down the choose from, and then over on the right hand side I want to compare the men and women. So I want that, and you literally drag it upwards. So you click on that little icon and drag it into this box here. That's the distribution variable. The split variable is gender. So there's this little thing up here that says split variable, and I'm going to put gender into that. I want to split the graph by gender, and I want warmth as my distribution variable. So I've dragged warmth into that box, and I've dragged gender into that box. It'd be useful to put a normal distribution curve in. So I've clicked that box up, the tiny little box up there, and then I'm going to click OK. And now you can see that this data, we've done all these t-tests and heaven knows what, but the data is not particularly normal, is it? Lots of people have clicked 4s for everything. Lots of people have been lazy, and that's typical. That's typical. And you've got a choice as a researcher. You can say, I want to drop those people, I want to cut them out. But it's data. What do you do with that? What do you do with it? It takes a while to do it. So if you want to compare these, copy, Word, paste, and it will allow me to spin it. You can't do it within SPSS. I think it's a little bit easier to see, but although that distribution curve is not a bad fit to the female data and to the male data, it's not perfect, but we can now see why there's a difference. The male data is just slightly different from the female data, but the differences are very small. The differences are very small when you look at that distribution. But statistically, it's significant at 0.302. Really, really significant. So always check, because you look at this and you realise why people are a bit nervous about using 95% confidence limits. We are 2 chances in 1,000 confident here that there's a difference between men and women. So when you look at the data, you think, really? Really? And one reason it's a big sample. So Coco, when you do your analysis, you're never going to get differences as big as this on a sample of 20. And if you do get significant differences, graph them out just to make sure what's happening here, and then decide whether or not you're happy. Let's go back to the graph. Where are we? That's the data. So I want to graphs, chart builder. So I just want to look at the distribution. I would click on histogram, drag it into there. Let me redo it. Reset. Okay. Click on histogram. I just want the normal distribution, and I just want warmth. And OK. I'll now get just that simple distribution. That's male and female data combined. I've got means and standard deviations up here. Really shows you this problem with people ticking 4 boxes, which is the middle point on the scale, 7-point scale. You take things out like that. Yeah. So I think the chart builder, legacy dialogues, there's lots of simpler ways of doing it. So if you get stuck, if you really get frustrated, it's 2 o'clock in the morning, you need to have this graph done, drop down to legacy dialogues, and these are somewhat easier. But once you've invested a couple of months learning what the heck this does and what it doesn't do, it's fantastic. So, what we've been playing with so far is that we're pretty happy that there's some interesting differences between the way people have evaluated warmth, but only because of their gender. What we haven't done anything so far is to look to see if there's any differences by whether or not they receive the signal of small company, family business, or both together. I can do t-tests for that. So I can use analyze, compare means, independent sample t-test, and instead of warmth I can click on family signaled or not. I've got to get rid of gender, family signaled or not, and I think the groups are 0 and 1. So it's telling me just on its own there's a not particularly significant difference between telling people it's family or not telling it's family. If I look at small, compare means, independent sample t-tests, small or not, define groups, same one, it's telling me there is a significant difference. So it looks as if signalling small is more powerful than signalling family. Both give you a positive result if you look at the means, but only one, small, gives you a significant result. Not surprising then that when we submitted this paper to journals specialising in family business, they weren't too pleased. They weren't too pleased. So the next time we submit it, it will be to a small business journal. But I've not done the fancy analysis. I've not looked to see whether or not there's a different sort of analysis. So this is now going to be a two-way Anova. And I'm going to use the fact that I've got a box with 4 bits in it. In this box, that's the mean score for warmth for the people who were not told family owned and not told small. So they weren't told anything. They weren't told family owned, they weren't told small. On the right hand side at the top, they were told family owned, but they weren't told small. Coming down on the left hand side, they were told small, but not family owned. And in the bottom right hand box, they were told both. And I want to know what is significant about that, if anything. And to use that, I use something called two-way Anova. And all two-way Anova is a series of t-tests. So it tests the bottom row against the top row, the left-hand column against the right-hand column, and the diagonal. To see what's going on here. So let's go back into the data. This one is the most difficult to remember out of all the ones that we're going to look at, because it's counterintuitive. Analyze, general linear model, univariate. Nowhere does it tell you two-way Anova. So general linear model, univariate. The dependent variable, warmth. So we click on that, shove it in there, and then the fixed factors are told family or not, size or not. Now these variables are binary, 0 or 1. They were told or they weren't told. There's no fancy numbers in. So it's really odd. Then click OK. And we get the usual statistics. many in each cell, blah, 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 blah. And now some interesting stuff. So we're trying to predict warmth, and the independent variables are family or not, small or not, and family or not times small or not. So-called interaction effect. And looking across here, now when you chuck them all in together, we get significant results from all three. So if we go back to this, that is significant, that is significant, and that is significant. So moving from the baseline out, telling people family, telling people small, telling people both, all of those three are actually significant, is what we're being told. But we know that men and women have reacted differently to warmth. So we've got to put gender in as well. Oh God, I hope it helps rather than makes a mess. So how do we do that? Analyse general linear model univariate, and we put gender in as a covariate. So we're looking at the effect of gender on warmth and taking that away from everything else. Click OK. Gender, highly significant, 0.002. If you compare this box with this box, it actually improves things. It makes the significant figures slightly better. 0.33, 033 on family or not, improves to 0.023. So what do we conclude from this? When it comes to signaling warmth, you can signal small, you can signal family, or you can signal both. It doesn't make a blind bit of difference to improve your warmth image in the marketplace. And that's what Deanne will be doing if he goes. So, analyse general linear models univariate, and I want to plot this. So family or not on the bottom axis, small or not on the other axis. Continue. Whoops. Didn't do that right. Family or not, small or not, add. Continue. OK. So this shows the whole thing graphically now. So down here, this data point is not told size and not told family. Blue line. If we tell family, the warmth figure goes shooting up. If not told family, but told small, we're already up there, and telling family doesn't improve things. And sometimes when you show people the graphic version of that, it's easier to understand what the heck's going on. So, Two-Way Anova, the sort of thing that we've just been looking at, that experimental design, was very commonly used to test pharmaceuticals. Because you're dealing with fairly small numbers, you're giving people a drug, and you're not too sure whether it's going to be good for them or bad for them. You tend to test on people in South America, poor people that will do anything for a lot of money, very unethical. And then you test those small samples using techniques like the ones that we've just been looking at. Now this is starting to come across to management research. So we can use t-tests, we can use correlations to analyse the relationship between dependent and independent variables, but here is extremely scientific because one group have been told absolutely nothing and then you just tell another group, a matched group of people, this business is a family business, or whatever you want to tell them. So that is probably state of the art when it comes to management research at the moment, so-called experimental design. It's been there for about 5 to 10 years, and it'll last another 5 to 10 years before something else comes in and takes over. So structural equation modelling, which I could have shown you today, getting a bit old hat now, still useful. If you want me to run a session on that sometime, happy to do so. But I thought experimental design is probably where it's at. If you want to understand more about experimental design, there are a couple of books. There's resources online. You just type experimental design. But if you've understood what I've gone through today, then great. Now, I'm saying that these are fantastic results, but they're only 95% confident. What we need is theory. So if you have theory plus 95% confident, you're confident. You're confident. And that's why you need theory and the stats. Because there's a 5% chance that the analysis will show you something which is rubbish. But if you've got theory, well, now Wing and I differ in the way we go about research. Wing is much more careful than I am. She wants the theory first. I know, let's see what the data says and then we'll go and find the theory.
Well, it depends. It's quantitative data. I go the other way as well.
Yeah.
Qualitative.
Yeah, but it can be dangerous. It can be dangerous.